In this lecture, we are going to discuss the GCD of more than two integers and its properties. In the previous lectures, we discussed the GCD of two integers. Now we are going to discuss the GCD of more than two positive integers. The GCD of n positive integers a1, a2, etc. an, where n is greater than or equal to 2, is the largest positive integer that divides each ai, and it is denoted by this symbol. So the GCD of n positive integers a1, a2, etc. an is the largest positive integer that divide each of these integers. For example, find the GCD of 12, 18 and 28. The largest positive integer that divides 12, 18 and 28 is 2, because we have from these numbers 12, 18 and 28, the smallest number is 12. The factors of 12 are 1, 2, 3, 4, 6 and 12. So the largest divisor is 12, but 12 does not divide 18. So this is not the largest positive integer that divides these three. Next is 6. It divides 12 and 18, but it does not divide 28. So this is not the largest divisor. Next is 4. 4 divides 12, but 4 does not divide 18. So this is not the largest. Then 3. 3 divides 12, 3 divides 18, but 3 does not divide 28. So this is also not the largest one. Now what about 2? 2 divides 12, 18 and 28. So the largest positive integer that divides 12, 18 and 28 is 2. So we have the GCD of 12, 18 and 28 is equal to 2. Now next one is 12, 36, 60 and 18. So here also the smallest one is 12. So these are the divisors. Now what about 12? 12 divides 12 and 12 divides 36, 12 divides 60 and 12 divides 108. So 12 is the largest factor of 12 which divides 12, 36, 60 and 108. So GCD of these numbers is equal to 12. Now next one is 15, 28 and 50. So if you are checking the factors of 15, we have 1, 3, 5 and 15. These are the factors of 15. Now if you are taking the largest one, 15 divides 15, but 15 does not divide 28. So this is not the GCD. Now what about 5? 5 divides 15 and 5 divides 50, but 5 does not divide 28. So this is not the GCD. Now 3 divides 15, 3 does not divide 28. So this is also not the GCD. Now it is 1. So 1 divides 15, 28 and 50. So the largest common factor is 1, and so that is the GCD. Now a linear combination of n positive integers. A linear combination of n positive integers a1, a2, etc. an is a sum of the form alpha a1 plus alpha 2 a2 plus etc. alpha n an, where alpha 1, alpha 2, etc. alpha n are integers. This is just as in the case of two integers. So for example, minus 1 into 12 plus 1 into 15 plus 0 into 12, 21 is a linear combination of 12, 15 and 21. This is another linear combination of 12, 15 and 21, taking alpha 1 is equal to 3, alpha 2 equal to minus 2 and alpha 3 equal to minus 5. Now next we have a theorem. The GCD of the positive integers a1, a2, etc. an is the least positive integer that is a linear combination of a1, a2, etc. an. That is, the GCD of these positive integers is the least positive integer that is a linear combination of these numbers. I am leaving the proof of this theorem to you. Now for example, express 12, 15 and 21 as a linear combination of 12, 15 and 21. We know the GCD of 12, 15 and 21 is equal to 3. So we have to express the GCD of these numbers as a linear combination of 12, 15 and 21. That means here GCD is 3. So we have to express 3 as a linear combination of 12, 15 and 21. So we need to find the integers alpha, beta and gamma such that alpha into 12 plus beta into 15 plus gamma into 21 equal to 3. So by trial and error we'll get alpha equal to minus 1, beta equal to 1 and gamma equal to 0 is such a combination because minus 1 into 12 plus 1 into 15 plus 0 into 21 is equal to 3. Okay. Next, the recursion can be used to find the GCD of 3 or more integers. This theorem shows how recursion can be used to find the GCD of 3 or more integers. Theorem 3.10 is let a1, a2, etc. an be n positive integers when n is greater than or equal to 3. Then the GCD of a1, a2, etc. an is equal to GCD of a1, a2, etc. an minus 1, comma an. That is, if you need to find the GCD of 1, 5, 7, 10, 12, you can just use this GCD of 1, 5, 7, 10, comma 12, and this is equal to GCD of, this can be written as GCD of 1, comma 7, comma 10, comma 12, etc. In this way, by using recursion, we can find the GCD of n positive integers. The proof is simple here. Let d equal to the GCD of a1, a2, etc. an. D dash is equal to GCD of a1, a2, etc. an minus 1, and d double dash is equal to GCD of d dash comma an. So g double dash is equal to, actually we have, this is d and this is d double dash, because we have d dash is this a1, a2, etc. an minus 1, and d double dash is d dash comma an, that is this. So we need to prove that d equal to d double dash. So we are going to prove that. To prove this, we are going to prove that d divides d double dash and d double dash divides c. So from this we get d equal to d double dash. So first we are going to show that d divides d double dash. Since d equal to the GCD of a1, a2, etc. an, we have d divides a1, d divides a2, etc. D divides an. That is, d divides ai for every I. This is by the definition of the GCD. So we have d divides d dash, because d dash is actually the GCD of a1, a2, etc. an minus 1. So since d divides each ai, that is, d divides a1, d divides a2, etc. d divides an. So d divides d dash. Okay, because d dash is the GCD of a1, a2, etc. an minus 1, and also we have d divides an. So we get d divides d dash comma an. D divides the GCD of d dash comma an. So we have d divides d double dash. Now to show that d double dash divides d. Since d double dash is equal to GCD of d dash comma an, we have, by the definition of GCD, d double dash divides d dash and d double dash divides an. So d double dash divides d dash implies d double dash divides ai for I between 1 and n minus 1. That is, d double dash divides a1, d double dash divides a2, etc. d double dash divides a n minus 1. Also we have d double dash divides an. So we have d double dash divides ai for I equal to 1 to n. Therefore d double dash divides ai for I from 1 to n. So we have d divides d, because d is the GCD of a1, a2, etc. a. So d divides d double dash divides d. Therefore we have d divides d double dash and d double dash divides d. Therefore we have d equal to d double dash. Therefore we have this is equal to this. Now, for example, using recursion, evaluate the GCD of 18, 30, 60, 75 and 132. By previous theorem, we have GCD of these numbers is equal to GCD of 18, 30, 60, 75 and 132. GCD of these two numbers were, this is the GCD of 18, 30, 60 and 75 only. And applying again the theorem, we will get this GCD can be written as GCD of 18, 30, 60, comma 70, 75. Okay. Now again this can be written as GCD of 18, 30, 60. Again this we have GCD of, now we have to find this GCD first. So GCD of 18, 30, it is nothing but 6, because devices of 18 are 1, 2, 3, then 6, 9 and 18. So 18, if you are taking 18, 18 divides 18, but 18 does not divide 30, so this is not the divisor of this. 9, if you are taking 9, 9 divides 18, but 9 does not divide 30, so this is not the divisor, GCD. Next is 6, 6 divides 18 and 6 divides 30, so 6 is the GCD of this 18 and 30. Now we have to find GCD of 6, 60, then 75, then 132. Now that is this GCD of 6, 30, 60, that is 6 itself. So because this is the greatest, that is the greatest divisor of 6, which also divides 60, is nothing but 6. So 6 is the greatest GCD of 6 and 60. Now we have to find this 6, 75. GCD of 6, 75 is 3. This is 3. So 3, 132. That is GCD of 3, 132 is 3 itself, because 3 is a divisor of 132 also. So the GCD of these numbers is equal to 3. Next we have pairwise relatively prime integers. That is, the positive integers a1, a2, etc. an are pairwise relatively prime if every pair of integers is relatively prime. If you have more than two positive integers, then which are called pairwise relatively prime if every pair of integers is relatively prime. That means ai aj equal to 1 whenever I not equal to j. That means the GCD of a1 a2 equal to 1, or a1 a3 equal to 1, etc. a1 an is equal to 1, and then a2 a1 a2 a3 a3 a2 a4 etc. a2 an is equal to 1, etc. That is ai aj equal to GCD of ai aj equal to 1 whenever I not equal to j. Then we can say that a1 a2 etc. an are pairwise relatively prime. That means if you are taking any two of that integers, then that will be relatively prime to each other. For example, 8, 15 and 49 are pairwise relatively prime because we have the GCD of 8 and 15 is equal to 1. The GCD of 8 and 49 is equal to 1, and GCD of 15, 49 is also 1. So if you are taking any pair of numbers from these three, we will get which are relatively prime to each other. So 8, 5 and 49 are pairwise relatively prime. Now what about this 6, 25, 77, 99? These are not pairwise relatively prime because here we have 6, 25. The GCD of 6, 25 is 1. Also GCD of 6, 77 is also 1, but GCD of 77, 91 is not equal to 1 because 7 is a factor of both of these numbers. 7 is a factor of 77 and 91. So GCD is not equal to 1 for 77 and 99. Therefore, these numbers 6, 25, 77 and 91 are not pairwise relatively prime. Next we have a corollary. If the positive integers a1, a2, etc. an are pairwise relatively prime, then their GCD is equal to 1. If the positive integers a1, a2, etc. an are pairwise relatively prime, then their GCD is equal to 1. For example, 8, 15, 49 are pairwise relatively prime because we have GCD of 8, 15 equal to 1, GCD of 8, 49 equal to 1, and GCD of 15, 49 is equal to 1. So these three numbers are pairwise relatively prime. Therefore, their GCD is equal to 1 by using this corollary. But the converse of this above theorem is not true. That means a1, a2, GCD of a1, a2, etc. an is equal to 1 does not imply a1, a2, etc. an are pairwise relatively prime. That is no guarantee that The GCD of A1, A2, etc. An is equal to 1 implies A1, A2, etc. An are pairwise relatively prime. Because, for example, we have GCD of 6, 10 and 15 equal to 1 because we have the factors of 6 are 1, 2, 3, 6. So if you are taking 6, 6 is a factor of 6 but 6 is not a factor of 10. So this is not the GCD. Now if you are taking 3, 3 is a factor of 6 and 7 is 15 but it is not a factor of 10. So this is also not a not GCD. Now what about 2? 2 divides 6, 6 and 2 divides 10 but 2 does not divide 15. So this is also not GCD. But so 1 divides 6, 10 and 15. So 1 is the GCD of these three numbers. But these three numbers 6, 10, 15 are not pairwise relatively prime because GCD of 6 and 10 is equal to 2. It is not equal to 1. This GCD of 6 and 15 is equal to 3. It is not equal to 1. GCD of 10, 15 equal to 5. It's also not equal to 1. So the GCD of n numbers is equal to 1 does not imply the individual numbers are pairwise relatively prime. Next, we have an alternate proof of the infinitude of primes. That is, we already proved that there are infinitely many primes in the previous lectures. Here we are discussing another proof for this statement that is there are infinitely many primes. This is an alternate proof for this infinitude of primes. Suppose there is only a finite number of primes which are p1, p2, etc., pk. Consider the Fibonacci numbers fp1, fp2, etc., fpk. Clearly, these Fibonacci numbers are pairwise relatively prime. Since there are only k primes, each of these Fibonacci numbers has exactly one prime factor. Since there are only k number of primes, each of these Fibonacci numbers has exactly one prime factor. That means each of these Fibonacci numbers is a prime. But this is a contradiction because we have F19 is not a prime because F19 is equal to 4181 which is nothing but 37 into 113. Therefore, F19 is not a prime. So, this is a contradiction. Each of these is a prime is a contradiction. So our assumption that there are only finitely many primes is false. So this assumption is false. Therefore, there are infinitely many primes. So this is an alternate proof for this theorem.